Any extra, here you go. Sorry. I'm gonna need that. All right, that's 29. We're almost as full. This is it. If anybody comes next, they have to sit right in front of me. All right, so like I said, if hopefully you read all the emails and announcements, you should have looked at proton and carbon NMR by now. So we're going to just start with this. We're going to do this worksheet today. If you're watching at home, this will be in the module for chapter 14 and 15. This worksheet. We'll go through answers. I'll give you a little bit of time to do one. If you finish one, go on and do the next one. We'll talk about it eventually. Right now, this is open note, open book. Talk to your friends. Like ideally, what I would normally do in a non-pandemic semester is that I would group you together and let you go over it. That's, if you can talk to each other from 6 feet away, which I hope you're good at by now. Folks at home should work the worksheet. Obviously, you don't have to sit here and watch us just look at each other. So fast forward. So go ahead and start number 1. I'm just asking for how many different signals in the proton and the C13 NMR would appear. Yep. Anybody got an extra? There we go. Spread them out. Yeah. So I'll give you, I don't know, 5, 6, 7 minutes. If you have questions, I'm milling around and am happy to answer any questions. Like I said, if you get number 1 done, go to number 2, and then we'll get to that. Would that be 5 signals or 1 signal? That's the question, isn't it? Yes. It's neither 1 nor 5. Bless you. I think the first one's one you were. Yeah. those of you who are in your first spring in North Carolina, that's going to be a common sound. What's that? All right. So now that you've had a minute, now that you're just opening up and talking to each other, I hear noise, so I'll interrupt. So I'm going to do the first one. I'll do this first one first. We'll talk about this one, and then you can revise your answer to the next ones. All right. So I've put the molecular formula up there. I'm not asking you. This question is not asking how many protons are in the molecule or how many carbons are in the molecule. It's how many signals you'll see. All right, so first of all, proton NMR will only show signals for protons. We can't directly see any atoms except protons. You can infer from chemical shift if there's something electronegative or if there are double bonds or if there's hydrogen bonding, but you can't see it directly. In the carbon NMR, you can only see signals for C13 or for carbons. And then in a proton NMR, in a proton NMR, every proton has to be accounted for. All right? You can't just be like, well, that proton doesn't show up. Same thing in the carbon NMR. Every carbon has to be there. There will be a signal for every carbon. Okay, so the question here is how many different, magnetically different carbons are there? How many magnetically different hydrogens are there? And there's a couple of different ways to answer this question. You can look for symmetry, and you can also do what's called a replacement test. All right, so I'm going to do a replacement test on this molecule. Let's look at, so there are 5 aromatic hydrogens. All right, so there are 5 protons on that benzene ring. Each one of those protons is on an sp2 carbon. By the way, how many units of unsaturation in this molecule? 4. Right? 1, 2, 3 pi bonds and a ring, so 4 unsaturations. You can get that C10H14, if it was saturated, it would be CnH2n plus 2. So it would be C10H22. So we're missing 8 hydrogens. 8 divided by 2 is 4. Okay, so the question here is, I guess I'm gonna kind of assume you get that the aromatic hydrogens are different than the hydrogens on the sp3 carbons. Okay? But now, the other thing I'll show here is there's a plane of symmetry down the middle of this ring. All right? Any benzene that's got one substituent on it, right down the middle, if you include the carbon that's got the substituent, you'll have a plane of symmetry. So if we look at HA, let's just, here, A, B, C, D, and E. So if you look at HA and HE, this is the replacement test. All right, I just replaced HA with a D. D is deuterium. When you use the replacement test, you can kind of replace it with, you can replace the atom with anything. I like D because then it keeps it, you know, it's hydrogen, keeps it simple. All right. So in the replacement test, you're going to draw 2 molecules. You need to replace, not B, sorry, H, E. All right, so in the first molecule, I've replaced HA with D. In the second molecule, I'm replacing HE with D. All right, so those are the 2 structures I get. Now, in the second, so the first step of the replacement test is you replace the 2 atoms you're wondering about with the same atom. HA with D, HE with D. And then you ask yourself, what is the isomeric relationship here? All right, you guys remember number 4? I told you you should review it. I was serious. I meant to do that. All right, so what is the isomeric relationship? What? Are they? So if I take D, remember these sigma bonds, you can rotate around those freely. Okay? If I take the molecule on the right and I flip it over, I get the molecule on the left. This always bugs people here. Imagine this is just a methyl, right? It's easier to see that way. This group is going to freely rotate out here. So maybe you think they're conformational isomers. That's fine. But they're either the same or they're conformational isomers. And if that is the answer, then we would say, sorry. All right, so HA and HE, what this test tells you, the two structures I've drawn there are completely hypothetical. All right, they don't really exist. They're thought experiments. The fact that those two structures are the same, or if you like, they're conformational isomers of one another, means that the two atoms we tested, HA and HE, are called homotopic. What you would call that in English is the same. All right, those are the same protons. And you can see this, right? HA is on a carbon that's bonded to another aromatic benzene carbon that's got an isobutyl group on it. HE is bonded to an sp2 aromatic carbon that's next to an isobutyl group. Both of them are next to an sp2 atom with one proton, and then they're bonded to the same one. So HA and HE are the same. And that means those two protons are going to give you the same signal. So homotopic protons, another word for a homotopic proton is a magnetically equivalent proton. All right? Magnetically equivalent atoms, I should say. It's not just protons. Magnetically equivalent atoms will give you the same signal. They will not couple to each other. Right? They're just two of the same in that pot. All right, so if we do that same test, let's do HA and HB. So I've got HA replaced with B. I'm now doing HB. Right? Some of you were writing. I shouldn't go so fast, but so I've got this structure up here where I replaced HA with D. Down here in purple, I'm drawing what I get with replacing HB with D. All right, here, and now you compare these two structures, HA and HB, and now they're constitutional isomers, right? So if you look at this, HA is bonded to an sp2 aromatic carbon that's next to an aromatic carbon with an isobutyl group. HB is bonded to an aromatic carbon that's bonded to two aromatic carbons with H. HB is not the same as HA. So the answer here is, if you get constitutional isomers, these are heterotopic. Heterotopic atoms are magnetically non-equivalent. If they're neighbors of one another, and we'll get to that in a second, if they're neighbors of one another, they will couple to one another. They'll split each other's signals. Benzene rings are pretty easy. That's why there are three of the examples here. As you go around, so HA and HE, either side of that plane of symmetry, they're going to be homotopic. HB and HD, right? We can do that. So if we do HD, the letters get away from me. Right, so there's replacing HD with D, and now it's the same thing, right? This, if I take this structure and I flip it over there, I get the same structure. All right, so HB and HD are homotopic, one signal. And then HC is not like any of these. HC is directly across from the atom that's got the isobutyl group. None of the others are. So HA and HE, that's one signal. HB and HD, that's a second signal. And HC is a second signal. Third signal, sorry. Can't count. So how many? All right, so that's three signals from the aromatic group. How many from the isobutyl group? Anybody want to, do I hear some guesses? I got 3. 1, 2. Anybody, do I hear 4? 2? 3.14? All right, 3 is the answer. HF, HG, HH, HI, all right, that starts to be pretty complicated there. If you do the same replacement test, I'm going to erase some stuff here. So if I replace HF with D, I get that, right? Replace the wedged HF, HG with D. All right, what is the relationship of those two molecules? What's that? Are they diastereomers? They're enantiomers. Right? So again, this is not a chiral center here. 2 methyls. All right, so these are enantiomers. All right, so enantiomers. Enantiomers, are they magnetically equivalent or non-equivalent? They're equivalent. All right, there's not necessarily an easy answer to that. Yeah. If the result of this replacement test, so if the result of the replacement test gives you 2 structures that are enantiomers of one another, the two atoms are said to be enantiotopic. All right? So again, going back to chapter 5, enantiomers have equivalent energies. Enantiomers have the same energy. They're equally stable. The only way to differentiate enantiomers is if you have something chiral come in. So if I'm just like hydroxide and I'm going to pull one of these H's off the molecule, hydroxide's not chiral, it's going to pull either one of them off. Right? HH and HG will react identically to an achiral reagent. If I'm an enzyme, if I'm a chiral enzyme and I'm coming in to pull a proton off, I'll actually pick one or the other there. Okay? So somebody said diastereotopic. I don't have an example here. Diastereotopic atoms are magnetically non-equivalent. All right? Diastereomers can have different energies. Again, think back to exam 1. If I've got a cyclohexane with all the substituents equatorial, a diastereomer may have 2 equatorial and 1 axial. Right? That's different energies. Those are going to have different stabilities. All right? So magnetically equivalent atoms are either going to be homotopic or enantiotopic. Magnetically non-equivalent atoms are going to be either heterotopic, that is different, or diastereotopic. So, had this been a chiral center here, right, let's just do a kind of, again, a thought experiment. This is a different, this is not, there's not a molecule on the board that looks like this, but right, if we had a chiral alcohol that kind of looked the same, right? On our real molecule, these 2 groups are methyls. The 2 methyls, in fact, are enantiotopic. So those 2 methyls are going to give you the same signal. All 6 of those protons will be magnetically equivalent. So these 6 on the top on our real molecule, right, are going to give the same signal. They'll have one neighbor, so they'll be split into a doublet. Again, more on that in a second. In the bottom molecule, right, an OH and a methyl, they're not the same, so this is now a chiral atom. The carbon that the OH is on is a chiral atom. That means if we, on this position, if we had HF and HG on that CH2 position, replacing one with D and replacing the other with D gives us 2 diastereomers. Right? So now, down here, the 2 protons on this position would be diastereotopic. And if you think about that, so that means they're magnetically non-equivalent. That means they give different signals. They can couple to one another. And if you think about that, right, the proton that's wedged is kind of looking across at an OH. The proton that's dashed is not looking across at an OH. They can't ever, those 2 hydrogens can never be in really exactly the same electronic situation. All right? Okay, so for this top molecule, we get, the answer is 1, 2, 3, 4, 5, 6. All right, so HC is unique in the molecule. HB and HD are magnetically equivalent. HA and HE are magnetically equivalent. HF and HG are magnetically equivalent. HH is unique. HI and HJ are magnetically equivalent. So there are 6 signals. What about carbons? How many carbons do we have? I'll give you like 30 seconds to think about how many carbons we have. Anybody with a guess? We have a vote for 7. Anybody want to fight him? I mean, disagree respectfully. All right, good. 7. 7, I think, is the answer. It's amazing. So you're very brave to speak up. And I never spoke in class. I mean, organic I was really good. A lot of classes I wasn't. Treated them all the same. I was going to stay silent. So thanks to those of you who are willing to speak up. Even now, like I was completely convinced, and as soon as I came over here to like illustrate it, I'm like, oh crap, really? Is it 7? I don't know. So the thing to think about here is the same plane of symmetry is going to exist. So the carbon with the HA and the carbon with the HE, if HA and HE are equivalent, then those 2 carbons need to be equivalent, and they are. Right? So this carbon with HC, the B and D carbons, that's 2. A and E are the same, or magnetically equivalent, that's 3. Don't forget the carbon that doesn't have an H. All right? Every carbon will show up in the C13 NMR. Every proton will show up in the proton NMR. And that's all that will show up. All right? You won't just get... I think I said this in one of the PowerPoint shows. Spectroscopy is probably the part of organic chemistry that is the most broadly applicable to just doing science. Don't take more from the data than is there. And also don't invent stuff, right? If you have a spectrum, if we thought it was this molecule and my spectrum has 8 signals in it, that's not the molecule. Or I've got to come up with a reason there's an 8th signal. So 1, 2, 3, 4, 5, right? That sp3 carbon has 2 H's. There are no other sp3 carbons with 2 H's. 6, again, sp3 carbon with 1 H, none of those, no other ones in the molecule. And then the 2 methyl carbons, the 2 methyls are enantiotopic. Those 2 carbons are enantiotopic. So they're magnetically equivalent. That's the 7th signal. That sounds vaguely horror filmish, doesn't it? The 7th signal. Okay. So now what I'd like to do, that took a little longer than I expected. I'm going to put up an answer for the others while you work number 2 for this first molecule. All right, so number 2 is predict the chemical shift and splitting for each proton in the 4 molecules in number 1. Do that first. Do this molecule that we've just been talking about. All right. And I'll put in an answer. I'll tell you what, is there anyone who's not finished the first doing what we just did for the first all 4 of those top molecules? Okay. I will post a key to this work set. All right. So go ahead and do number 2. Couple more minutes. Don't look at that. Work. Someone stole our magnetic erasers. You guys are quieter on this one. No neighbors, no anything? All right, like 60 more seconds. A lot of folks are staring at me, so. Okay, so I've redrawn that molecule, trying to clear up the groupings. I didn't really go into it, but all three, anytime, it's kind of like, if you remember in the spectroscopy, I said that methyl protons are never going to be, like a methyl's never chiral, it's got 3 protons on it. By the same count, the 3 methyl protons will always be homotopic, right? The 3 protons in a methyl will always give the same signal. If there were another chiral molecule, like if there was a chiral center here, these 2 methyls now might be diastereotopic. Yeah, they would be. So you'd see different ones. If you didn't notice that from the first, what we did there at first, the less symmetrical a molecule is, the messier its spectrum is going to be. Okay, so if you have a chiral center in a molecule, all of a sudden sort of almost every proton is different or magnetically non-equivalent. Methyls can be magnetically non-equivalent. But the 3 protons on a methyl will always be homotopic. Okay, so the book has a lot of numbers. And again, if you're someone that memorizes numbers easily, that's great. I memorize numbers okay, but largely I memorize numbers I use a lot. Right? I can still tell you my telephone number from when I was 8. I can't tell you my wife's current telephone number, right? Because she's in as Mary. I click Mary. It's going to get me in trouble one of these days. If you don't like memorizing numbers, try to memorize the regions. This is basically what I want you guys to know by exam 2, right? So carboxylic acids, the OH is going to sort of come. This thing can really come sort of all over the place, out to 15. It moves around a lot. Anything that hydrogen bonds in IR or proton NMR is going to be a very broad signal. That BS there means broad singlet. It's my favorite abbreviation probably in the class. So it's going to be broad. and it can kind of come anywhere. The more water that's in there, the concentration of water moves the signal, the concentration of the acid itself moves the signal. And this tends to be true for OHs generally. All right, so OHs and NHs tend to have a very variable chemical shift, and they tend to be quite broad signals. Often you don't see coupling to NHs or OHs. OHs and NHs are basically pretty unreliable. They need to be there. You need to see the signal for them, right? If my molecule has an OH, that H has to show up in the proton NMR. But it can come almost anywhere. It could be broad. It could couple. It could not couple. It's hard to say. All right, so OH is way out downfield to the left. Aldehyde protons, that's an H bonded to a carbonyl. That's going to be a much sharper signal because it doesn't hydrogen bond. But it's still bonded to a partial positive carbon, right? So if you notice the downfield, what I call de-shielded, what everyone calls de-shielded, means that that proton is having the electron density in the bond it shares pulled away from it. All right, so what I don't want to do, I could teach 2 or 3 lectures on just how an NMR works, how taking an NMR spectrum works. The short of it is you're putting this sample into an extremely powerful magnetic field. Any magnetically active nucleus is lining up with that field. Right? You guys have all done, like when you were 6, you'd magnetized a paper clip and dropped it into water or something. I don't know if you did that or not. A lot of people do. And it lines up with Earth's magnetic field. The NMR field is way more intense than Earth's magnetic field. Okay? So all the protons line up with the field you put it in. If you pulse it at just the right energy, it turns against the field. All right? So that's kind of, it's a little counterintuitive. Like lined up with the field makes sense. Right? It's always easier to go downstream than upstream. But if you think about it in that terms, like rowing down a river, canoeing, kayaking, canoeing down a river, right? Just kind of going with the flow is the easiest thing to do. The next easiest thing to do is to go straight up the river. It's hard work, but you don't have to worry about, aim. You just go against it. Going side to side can be really tricky. So these protons, they're either lined up with, or if you hit them at the right energy, they turn exactly against. And then in the NMR, what we listen for is that proton turning back to be aligned with the field. All right? And the energy gap between aligned with and aligned against depends on the local magnetic field in the molecule. So the electronic environment around it. The more electron densities around that proton, the stronger the current. It's shielded from the external field. The less electron density, right? Carboxylic acid, this carbonyl, the oxygen, they're all pulling electrons away from that H. That H is kind of naked by itself. It feels the external field entirely. I'm not going to ask you any questions about the physics of taking an NMR. All right? It's fun. It's cool if you like it. Take PChem. Chem 334, you'll use the NMR a lot. It doesn't like that. You don't need that right now. I'll get that back up in a second. Okay. So chemical shift is basically just frequency put into an easier to use axis. Good, there I am in Chile. All right, so the more electron density that's pulled away from the H, the farther to the left it appears. But it's not just quite as easy as memorizing that. You've got a region in here for aromatic protons. I want to emphasize this is a 6-membered ring with 3 double bonds in it. It's not just a 6-membered ring. All right? 6-membered rings aren't aromatic. Benzenes are aromatic. 6-membered ring with 3 double bonds. I'm going to, before something comes up that distracts you. There, look at a solar eclipse. All right. The reason I say not to memorize numbers is, I don't know why textbooks do this. They feel like they have to give you numbers, and people like numbers. That is 114.2, even though you can't measure it that accurately, right? So I've given you ranges here. You can just sort of memorize the order they come. If you like numbers better, memorize the numbers. But here we've got benzene, sort of 6.5 to 8.5. Protons on double bonds that aren't benzenes, so alkenes, kind of come 5 to 7.5. Protons on sp3 carbons, say this here. Protons on sp3 carbons that are bonded to something electronegative. Chlorine, oxygen, nitrogen, bromine. That's going to kind of come 3 to 5.5. Protons on an sp3 carbon that are bonded to an sp2 carbon come 2 to 3. And then protons that are just kind of on sp3 carbons bonded to other sp3 carbons, you know, the workhorse, the alkane, the hydrocarbon, those are like 0 to 2. That's all you need to know. There are way more numbers you could know, and you could know it like 5.4 to 7.8, but all that is hard to stick in your head, I think. Okay, so if we look at this then, let's plot let's just try to predict where each of the letters comes. All right, then we'll do splitting. So aromatic, 6.5 to 8.5. So HA, HB, HC, right? So there's 2 HAs, there's 2 HBs, and there's an HC. And those are going to come kind of in the aromatic area. All right, at this point, honestly, even for myself, don't get carried away with this one is 7.2, and that one's 7.28, and that one's 7.41. They come 6.5 to 8.5. All right, that's all I want you to know at this point. Oh, the other thing over here I put up that may not be obviously clear, in these regions, so this is talking more about the sp3 carbons, a CH will be downfield of a CH2, will be downfield of a CH3, all things being equal. Make sure all things are equal. I'm glad to have that on tape. It's like a possessed classroom, isn't it? All right, so if we look down here, this is all just sort of sp3 carbons bonded to other carbons. But there's one in particular, HF and HG, proton on an sp3 carbon bonded to an sp2 carbon. So HF and HG would come right in there. Yep. So CH3s are, why did you think CH3? That's sp3, right? So all of those are sp3. So F and G are on an sp3 carbon, and that sp3 carbon's bonded to an sp2 carbon. Yeah, okay. And then sp3 carbon bonded to other sp3 carbons, sp3 carbon bonded to other sp3 carbons. But a CH is going to be a little downfield of a methyl, right? So that's chemical shift-wise, that's where our atoms are going to be. And I've covered up the board I was going to use for splitting. Questions about that? More questions about that? All right. So the shape of the signal, in a proton NMR, the signal is usually not just a line. Carbon NMR, it's a long story. You're welcome to read about it in chapter 15. I'm not going to ask you any questions about it. Carbon NMR should couple, like a magnetically active carbon, the only magnetically active carbon is C13. C13 is only about 1% of the carbon on Earth. All right, so all the C12 in a molecule is just not magnetically active. So it doesn't care about the external magnetic field. The C13 nucleus will actually line up just like a proton. And then, like I said, these are magnets, so magnets interact with each other. So if a C13 is bonded to a proton, those are both magnets. They will influence how each other experience the external magnetic field. All right? We say that those are coupled. If two magnetically active atoms influence each other's magnetic fields, we say that those atoms are coupled, and they split the signal. Most carbon, like in this molecule, every carbon, there's this carbon right here that doesn't have any protons on it. All right, so every C13, and I guess I should say that, there's 10 carbons in that molecule. Odds are about every 10th molecule will have one C13 in it. And you might think there's no way you'll ever get a useful signal out of that. Except remember, you've got like 10 to the 23rd molecules. All right? When you have that many molecules, you can take a low abundance of isotope and still see a signal. So it's very unlikely that you're ever going to have a molecule that's got two C13s bonded to each other. That is statistically really unlikely. But every C13, except one in this molecule, would be bonded to a proton. So if we run a C13 and we don't do something to get rid of that coupling, then all those carbons show up as hairy lines. So when we run a carbon NMR, we basically, at the same time, excite all the protons to line them up with the magnetic field, and that makes sure they're all lined the same way, and now you don't see any coupling. Again, I'm not going to ask you about the physics in this class. I love the physics. I would love to talk about the physics for weeks. Okay, so those of you, nobody in here was. The poor folks that got me when we went online, and it was Zoom, and I could just sort of go off on tangents in my garage, you got to hear a lot about it. In here, what I'm going to ask you to do is work the sort of problems that are on this worksheet, and like I said, by the final exam, I want you to be able to take all the different spectra we have and come up with a molecule. Okay. So, looking at the proton NMRs, right, He is a magnet. Hd is a magnet. They're magnetically non-equivalent. So I've essentially got two little magnets sitting beside each other. And they will influence each other. Right? So if I want to look at the signal for He, right, the frequency with which He resonates depends on the strength of the external magnetic field that He feels. And so if Hd is aligned with that external magnetic field, it adds to it a little bit. If Hd is aligned against the external magnetic field, it takes away a little bit. The result is He is going to see two different, like some Hes will see one field and some Hes will see a different field. All right, again, that's all the physics. The rule comes down to the simple, I should say this is simple splitting. I know everybody always rolls their eyes at me. All right, the number of signals you see, the number of, not number of signals, sorry, hang on. Number of peaks. The number of peaks in a signal is equal to the number of neighbors plus 1. All right, that plus 1, the proton itself, by itself, if it has no neighbors, will show up as a line. Okay? If you have one neighbor, right, that neighbor could reinforce the external field or it could oppose the external field. 2 levels. If I have 2 neighbors, they could both reinforce, they could both oppose, one could reinforce, one could oppose. 3 levels. So the number of peaks in a signal will be the number of near neighbors plus 1. That's at a simplest go. And so you need a definition for neighbors. A neighbor is another proton within 3 sigma bonds. So a double bond only counts once. All right. And I have this, crap. All right, so I have this written over here too. Magnetically equivalent protons will not couple with each other. All right, my wife is not my neighbor. She's also, we're magnetically equivalent, if you want to say that. We're not homotopic, we're enantiotopic. All right, but she lives with me. She's not my neighbor. Kendall and Jim, they're my neighbors. All right? Okay, so number of neighbors is protons within 3 sigma bonds. So let's do one of these for real. Let's look at HA and HE. Remember, HE and HE are magnetically equivalent. That means their signal has to be the same. Same number of neighbors. If they don't have the same number of neighbors, they're not magnetically equivalent. Okay, so how many protons are within 3 sigma bonds of HA? Take 15 seconds or so and think about it. All right. You holding with your answer? Good. What's that? We got votes for 1. Anybody disagree with 1? All right, so you can count them. So HA is here, 1 sigma bond to the carbon, 1 sigma bond in the double bond, 1 sigma bond there. HA and HB are separated by 3 sigma bonds. So that's 1. 1, 2, 3. That gets us to a carbon. The 3 sigma bonds have to separate the protons, not the carbon the protons are on. All right. 1, 2, 3 gets us to a carbon. And that's it. Well, wait. 1, 2, 3. Again, a carbon. So yeah, HA has 1 neighbor. Functionally, a neighbor is either going to be a diastereotopic proton on the same carbon, or it's going to be a proton on a carbon that's bonded to the carbon that H is on. All right? So HA has 1 neighbor. One plus 1, carry the 1, 2. All right, that's going to be a doublet. So HA is going to show up in here. Kind of cramming this together, aren't I? HA will be a doublet. Again, doublet is going to be 1 neighbor, and the neighbor can oppose or reinforce. 2 energy levels, equal chances, 50-50. If there are 2 neighbors, both oppose, both reinforce, 1 opposes, 1 reinforces, That's three chances, but no longer, sorry, three levels, but no longer equal chances. One opposed, one reinforced. There's two possibilities for that. So your triplet is going to be 1 to 2 to 1 in intensity. A quartet will be 1 to 3 to 3 to 1, so on. Follows Pascal's triangle. How many neighbors does HB have? This is like a covert operation all of a sudden. People are like, it's got 2. All right, so HB and HA have to be neighbors. We decided that HB is a neighbor of HA. So remember you got to remember my home life, right? Mary's my wife, we're not neighbors. We have one signal, one home. Kendall and Jim are my neighbors. That means I am Jim's neighbor. I am Kendall's neighbor, right? A neighboring relationship can't go one way. Think about your dorm room. You know, you're your neighbor's neighbor. Okay. So HB and HD have to be equivalent. HD better have 2 neighbors, and it does. So HB, 1, 2, 3. 1, 2, 3. So 2 neighbors there. All right, so HB will be a triplet. Both A and C could reinforce the external field. They could oppose the external field. Or one could reinforce and one could oppose. One reinforcing, one opposing, there's 2 different ways. A could reinforce and C oppose, or C could reinforce and A oppose. 50% chance one opposes, one reinforces. 25% chance they both oppose, 25% chance they both reinforce. 1 to 2 to 1. So we're going to get a triplet. This is going to be HB. All right. How many neighbors does HC have? 2 again, right? So again, if C is a neighbor of B, B's got to be a neighbor of C, and then D is actually the same as B. C has a neighbor there, so again, a triplet. I don't know if you noticed, I drew HC's triplet smaller than HB's. Why did I do that? What's that? Yeah, integration. The number, so in proton NMR, the intensity of a signal is proportional to the number of protons making the signal. That's called integration. Right? There are 2 HAs, there are 2 HBs, and there's 1 HC. So HA we would say is a doublet that integrates for 2 protons. HB we would say is a triplet that integrates for 2 hydrogens. HC is a triplet that integrates for 1. Now, the other thing I'll tell you, if I ask you to sketch an NMR, it's probably going to look like this. These are, 3 magnetically different groups of protons. But they are pretty similar, right? They're all aromatic protons. It's completely possible they all just line up on each other. In reality, this spectrum could actually be something like this. Doublet, triplet. You can't see anything there. This would integrate for 5, and we would call this a multiplet. A multiplet is just different than a singlet. A singlet is a line. Means there's 0 neighbors. A multiplet means there's a whole bunch of lines that overlap. Means there's neighbors on those protons, and those protons aren't the same, but they're similar. Multiplets are going to fit more, like if you think about you're trying to interpret a spectrum, right? So if you see a multiplet, that fits a whole lot more molecules than a doublet, a triplet, a triplet. But it's harder to sort of get a lead on. All right, but that's what a multiplet is. All right, so let's move down to HF and HG. How many neighbors do HF, how many neighbors, let me review English for a moment. How many neighbors does HF have? Got to vote for 1. Anybody else? All right, so again, if you review magnetic equivalence and non-equivalence down there, magnetically equivalent protons cannot be neighbors. Right? Same signal, they're not neighbors. You don't say, my wife, your roommate, whoever you share an abode with, right? You don't say they're your neighbors. So HF and HG are magnetically equivalent. They can't be each other's neighbors. They are within 3 sigma bonds. They're within 2 sigma bonds. If those are diastereotopic, that means they're magnetically non-equivalent. They will be neighbors of each other. All right, but in this case, HF and HG are equivalent. The one neighbor is HH. So 1 sigma bond, 2, 3. Going from HG to HH, or HI to HH, sorry, HF to HH, takes you 3 sigma bonds. To get out to I, 1, 2, 3, and then the bond there is 4. You might wonder why 3. It just works out that way pretty empirically. You might note also I said simple splitting. That implies this can get more complicated, which I know maybe right now you don't agree with, but it can. And I can find you molecules where you see protons coupled over 7, 8 sigma bonds. It takes a really rigid framework and kind of special conditions. But for you guys, just keep in mind number of peaks equals number of neighbors plus 1, and a neighbor is within 3 sigma bonds. So HF and HG, 1 neighbor, so it's going to be a doublet. What will it integrate for? 2. All right, so integration is always relative. But since we've got HC and HH that are going to integrate for 1, this one would be 2. In reality, the NMR would spit you out. It's called an integral because you're actually integrating the area under the peak. And you'll see this sort of titration curve. On the first NMR I ever took about 30 minutes to run. And it got printed off on this sheet. Like you didn't save it to disk. Nobody had a disk that could save that much data. And so it printed off, it was like a poster. I wish I had kept one. Probably worth some money at this point. And the computer would plot this kind of titration-like curve, and you'd go and you'd measure the heights of those. And then that gave you, the height might be 11.5 centimeters, and you had to find a proton that you thought was 1 and set that at 1 and multiply. Anyway, now the computer spits out. And the other thing I would say is, I don't know what you'll see in lab. I haven't seen the spectra we're going to share with you, but this probably won't be 2212. It will be 2.08, 1.97, 2.16. Use your thought. There's no 0.16 protons in a molecule. All right, HH. How many neighbors does HH have? Hang on, before anybody answers, let me, what do you think? All right, we got 2. 2 and 8 are different. Finally, some disagreement. Anybody want to say something other than 2 and 8? 3. Not a bad answer. I can see how we get to 2, 3, and 8. Anybody got another number? I think it'd be hard to come up with a different number. So I and J are magnetically equivalent, so you might think, oh, I is a neighbor, J is a neighbor, and F and G are equivalent, so that would be a neighbor. That would be 3. Or you might just think methyls and HF and HG and get 2. In fact, even though they're equivalent, you count all of them, right? So here, the 3 HIs could all be aligned with, could all be aligned against. 1 could be with, 2 against, 2 with, 1 against. A lot of different permutations there. And then the same is true for HJ, and the same is true for F and G. So, in fact, HH has 3, 6, 2, 8 neighbors. This is going to be a nonette. Goodness, can he draw a nonette? So triplet, yeah. So this is going to be, it follows Pascal's triangle. and this is going to integrate for 1. I've drawn it bigger so you can see it. And it's ugly, right? I don't grade on artwork in here. HH integrates for 1 because there's only one HH. It's got 8 neighbors, so there's going to be 9 peaks in that thing. All right, HI and HJ. How many neighbors do they have? I can help you out with this, maybe. I hear crickets. Like, I literally hear cricket. I'm not making fun of you guys. All right, how many neighbors does the HH have? 1. It's got 1. 1, 2, 3. J is too far away, and I and J can't be neighbors anyway because they're magnetically equivalent. F and G are too far away. 1, 2, 3, 4. So it's going to be a doublet. I and J will be a doublet. What will that signal integrate for? It will integrate for 6. All right, so there, you've sketched the proton NMR of this molecule. I want to make a couple of quick points before we head out. I want to make one, I don't know if you call this one quick point or 3 quick points. All right, in your proton NMR is going to give you by far more information than any of the other spectra that you see. All right, you can really honestly, in the lab, if we have a decent idea of what the product should be, when we get a product, we run a proton NMR. We just get a quick proton NMR. If it looks like what we think it's going to be, we don't really bother with the other spectroscopies. We should. Like, to publish new organic chemistry, if your compound has never been described before, you have to give a complete set of spectra for that molecule. All right, high-res mass spec, IR, UV if it's got conjugated pi bonds, proton carbon NMR, maybe some 2D NMR. Proton NMR gets more complicated than even what's in chapter 15. Okay, but a quick proton NMR, if you have a good idea of what it's going to be, will tell you a lot. A proton NMR gives you these 3 pieces of data. Chemical shift, right? That tells you the electronic environment of the proton. It gives you splitting. That is going to tell you how many protons are within 3 sigma bonds of the proton making the signal. And it gives you integration. That tells you how many protons are making that signal. All right, this is like highlight of the class here. You have to use all 3 of these. I don't know why, but I've been teaching this for a long time, and students always seem to like the first one that you come to understand, it's like a first crush, man. You're just like, I get splitting. I'm going to use splitting to solve everything. And you can't do it, okay? So when you're analyzing a proton NMR, or if you're predicting a proton NMR, you have to use all of these. I didn't get to C13. I can draw a pretty similar diagram for a C13 NMR, but C13 NMR only gives you chemical shift. It does not give you, so you're going to find out about the electronic environment. You won't find out how many carbons are next to it, how many protons are next to it, or how many there are. Okay? Just the chemical shift. So we did today with the first one in number 1, and we did number 2 for that one. Like I said, I'm going to put a key up for this. So if you're watching at home, or if you're here in class and you'll be here next time, what we're going to do, I'll have us do. Actually, next time I'm going to have a different set of molecules. So even if you're here today, if you're not here on Thursday, download this sheet. watch the video and go through it. But I'm going to do number 1 for a different molecule, and then we're going to do number 4 for a different molecule. All right? Because I can't do all this in one class. Any questions? I know a lot of you got to go. I got to go. Any questions before we break? All right, go enjoy the sunshine. Some of you go enjoy the sunshine and the lovely spring day, and some of you come to lab with me and we'll separate cyclohexane and toluene. They're really equivalent, those two. Sorry? For in here, not very far. Honestly, for all this, like, Spectra's been thrown at you guys pretty fast. What's that?
So it's still sinking in.
Yeah. I don't do much mass spec in lecture. I'm going to really emphasize NMR in here.
Okay. I'm good with that.
Yeah. So, well, you haven't seen it yet in lab. You bet. And so what I'm going to do is, hopefully, there will be a lot of work sets. Mass spec, basically what mass spec is going to give you is the molecular ion. What's the molecular weight of the molecule? Chlorine and bromine. Like, there really is no good spectroscopic technique other than mass spec for figuring out if you got a chlorine or bromine in it. So,
okay.
Yep.
Appreciate it.
Yep. You too.
Would we be able to meet for office hours at some point?
I posted office hours this morning.
Oh, okay.
Go look at the, yeah.
Yeah,
Yeah, I just,
the problem for, like you said, like, yeah, I actually still don't